From nationwide medical claims to internet-scale 3D scenes and even the hidden structure of overlapping signals, today's research is pushing AI beyond familiar limits. One paper shows how foundation models can unlock real-world evidence from billions of healthcare events. Another tackles the messy long tail of sparse photo collections to rebuild better 3D geometry, and a third reveals why attention can collapse when information overlaps and how to fix it. Stay with us as we unpack three very different papers with one big idea. Smarter AI comes from learning to see what standard models miss. Let's explore the first paper, Foundation Models to Unlock Real-World Evidence from Nationwide Medical Claims. Reclaim is a decoder-only transformer foundation model, trained from scratch on 43.8 billion claims events from more than 200 million market scan enrollees spanning 2008-2022, using a custom tokenization that compresses diagnoses, procedures, medications, enrollment, and gross payment into a 20,865 token vocabulary and monthly temporal resolution. The model was scaled to 140M, 700M, and 17B parameters, and then post-trained on 100,000 prompt response pairs for incident disease prediction. Across 1,208 ICD-10CM onset tasks, the post-trained Reclaim-L reached 75.6% mean ROC-AUC in retrospective evaluation and 67.9% prospectively, outperforming LightGBM by 9.2 percentage points and Delphi by 6.2 points overall, with especially large rare disease gains of plus 16.9 and plus 7.1 points respectively. Performance generalized to external EHR benchmarks, including EHR SHOT and YNHH, where Reclaim still led both baselines despite dataset shift. The model also improved next year expenditure forecasting, raising R-squared from 0.2835 to 0.365 inches retrospective testing and from 0.335 to 0.451 prospectively, while better identifying high-need, high-cost patients. In a target trial emulation over 7,246 patients, Reclaim embeddings reduced expected absolute systematic error in negative control outcomes to 0.01 to 0.08, corresponding to an average 72% bias reduction versus Delphi. The main novelty is that nationwide claims, not EHR notes or labs, can support scalable foundation model pre-training with transferable representations for prediction, cost modeling, and confounding adjustment. Let's explore the second paper, Long-Tail Internet Photo Reconstruction. Long-tail internet photo reconstruction argues that the dominant failure mode in internet-scale 3D is not dense landmark capture, but the long tail of sparse, weakly connected photo collections where CoLMAP and modern feed-forward models such as Pi3, DUST3R, and VGGT break down. The paper's main technical contribution is Megadepth X, a 1,865 scene 440K image dataset built by filtering megascenes with Mass3R, SFM plus Doppelganger plus classification, manually verifying geometry against Google Maps and satellite imagery, and refining depth with a new monocular depth-guided filter that uses Moji 2 priors to suppress transient objects and depth bleeding. To match the true observation regime of long-tail scenes, the authors define sparsity-aware sampling over the SFM view graph using Louvain community detection, an approximate Steiner tree, and a greedy selection rule that favors unseen view communities and larger camera baselines while preserving local reconstructability. Fine-tuning Pi3 and VGGT with this data and a mixed dense sparse sampling scheme improves reconstruction robustness most on hard scenes. On Megadepth X, Pi3 FT raises RRA at 5 from 75.31% to 86.4%, and RTA at 5 from 59.16% to 71%, while reducing mean rotation error from 12.21 degrees to 5.72 degrees. VGGT FT reaches 81,0,0,7% RRAA 250 and 65,59% RTA 250. The gains are largest on Doppelganger and extremely sparse scenes, where the model separates visually similar structures and reconstructs coherent geometry when CoLMAP registers 0 images, while largely preserving performance on standard benchmarks such as Real Estate 10K, DTU, SU scenes, and NRGBD. Let's explore the third paper, When Attention Collapses Residual Evidence Modeling for Compositional Inference. This paper identifies slot collapse as a structural failure of attention-based compositional inference under additive superposition, where every token contains multiple sources, and standard slot attention repeatedly assigns multiple slots to the same dominant component. The authors trace the pathology to memoryless attention. Because all slots reread the same unchanged input, gradients are dominated by high amplitude sources and drive shared fixed points across slots. Their proposed fix, residual evidence modeling, is implemented as evidence depletion, a sequential slot attention mechanism that maintains a per-token residual evidence scalar EC, injects it into the attention logits via a gamma log EM bias, and multiplicatively updates evidence after each slot with extiv max as in controlled synthetic benchmarks on overlapping sinusoids, Gaussian bumps, and multi-scale mixtures. Linear depletion reduced peak overlap from 0.22, 0.32 for vanilla slot attention, and 0.81, 0.97 for sequential attention to 0.01, 0.07, and up to order of magnitude drop in collapse. On the fuzz real audio separation benchmark, collapse fell from 0.29 to 0.05, a roughly 6 times reduction. On simulated LISA gravitational wave inference, under identical architecture, data, and losses, vanilla slot attention diverged with max active overlap 0.99 and flow NLL plus 7.1. Sequential attention improved NLL but still overlapped at 0.67. While evidence depletion reached overlap 0.08, flow NLL 6, and substantially better CRPS on frequency, amplitude, inclination, right ascension, and declination. The key novelty is that non-redundant allocation requires explicit residual accounting, not merely more capacity, sequential processing, or auxiliary diversity losses. That's a wrap on today's AI paper highlights. Thanks for watching.